Hi guys, today we will talk about the INA circuits because the INA circuits are very important in electronics in general, and we will analyze a bit the internal structure of the INA without going so much into details. But why should you use INA instead of the differential op-amp settings? Well, the differential op-amp settings, as you may know, has the classical resistor R1, R2. This is towards ground, R3, R4. And even though you put the condition for the CCMI condition, which this true resistance and this true resistance have to be the same, the CCMR will still be low. So it's always better to use INA because they also have a greater bandwidth and they have a lot of advantages which we will see in this video. So let's look at this INA. This is the INA. This is the structure of the INA 293, one of the most employed in power electronics. When, for instance, you have a buck converter and you put a shunt here, most of the time you put just a filter and your INA. Now, as you can see, the INA is made with it is made with this structure here. First, you have the load supply, which in our case is the buck converter. Then you have the circuitry for the bias, and you have this true resistor here, which I will explain later what this resistor will be used. Let's call them Rin. These are important. And then basically you have this MOSFET here, and all this circuit acts like a current to voltage converter. And basically the equation is that you put the load resistor, which is RL, and if you have the output voltage here, VO, let's keep the buffer because we don't care. It is just an impedance separator. It doesn't affect the equation. The output VO is basically given by the resistor RS times the load flowing into the shunt. So this is the load, IL, this is the shunt. This will cause the drop voltage. And now, times the ratio between R out over R in. So basically, most of the voltage current converter obeys this equation. This is another INA. This is INA 105, and this has a little bit of different equation, but the principle is the same. You have always the shunt resistor and a load flow into it. This will cause a drop voltage, and then you have the output current, which is equal to the difference between well, here the output current is not inserted, the shunt resistor is not inserted, but the concept is basically the same. In the equation, you always have the input resistor, which in this case it is a very old INA, but in the equation you have the Rin resistor, and you have also the load resistor RL. So another detail that you must not skip is the fact that we have the current feedback Opamp. This is very important, and it is the reason why you have the load resistor here, which normally in the Opamp you don't take into account. Now, why the current feedback and not the classical Opamp? The reason is very simple. Short answer: the gain does not depend on the gain does not depend on your RF resistor. So basically, you will have a graph like this. When instead, in the classical Opamp, as your gain increases, the bandwidth decreases. So you will mostly have something like this. This is the way of the classical Opamp, the classic Opamp, and this is the current feedback Opamp. Now, this is the short explanation. The long explanation is this. You start by studying how it is done, the current feedback Opamp at the inside. This is the plus input and this is the minus input. So basically inside it you have the compensation capacitor and the resistor to this is used to compensate the bandwidth, and you have the feedback resistor RF and the RG resistor. So after the long computation, you obtain something like this. This is a very long computation, but let's just keep this and let's go to the approximation. The bandwidth is this. A out is the amplification of the op-amp. C comp is the compensation capacitor, which is here, and RF over RG is the ratio between the feedback resistor over the ground resistor. It is basically this resistor here, RG and RF of the classical op-amp. Just to know. So you can approximate this bandwidth, the pole of this bandwidth, for low gain. If you do that, you get that the frequency of the pole is this. This is very important because you understand that the frequency of the pole depends only on the resistor of the feedback. Meaning that if you fix the resistor feedback 1 kilo ohm and you change this resistor, let's choose for instance 100 kilo ohm, and you fix this resistor here, RG, your gain will increase like this, but the bandwidth will not decrease. And you always cut at this point here. If you do that instead in the classical op-amp, as I said before, you will obtain something like this. So the gain will decrease. And I will show you this immediately, because we need to get to understand the importance of the current feedback op-amp. So we will now choose the LT6210. This is one of the most common programmable supply current current feedback amplifier. By biasing it by putting 1 kilo ohm resistor, this will not affect much the bandwidth. We will use the minus 50 volts as V minus, and plus 50 volts as V plus. Let me put the net, V plus and V minus. And let me put it here. So now let's fix the resistor RF like I did before. Like I explained before. Let's call this RF and let's put it to 100 kilo ohm. Now we want to change the gain according to this resistor R. Let's step it with the R. Let's write dot step param R list. Let us put 100 kilo ohm, 10 kilo ohm, 1 kilo ohm, and yes, 100 kilo ohm, 10 kilo ohm, 1 kilo ohm, and 100 ohm. Let's call this O2. And now let's do the same with the classical op-amp. Let's use the universal op-amp 1. Let's do the same here. Oops. I put V minus, I put exactly the contrary, V minus here and V plus here. And let's call this output O1. Let's put this to ground. for both the input. Ah, sorry, here I forgot the signal. Let me put this, and let me write AC1. We will do the same here, and we will put the resistor R fixed to, I don't care. Let me put this here, and let me use the negative feedback and put the classical gain R. R. And it is RF2. Now, as you may know, this equation is V naught equal to minus V in times RF2 over R3 in this case. So the gain is this resistor of this resistor here. Now, to study the bandwidth of this and to make you see that this converter, this op-amp will follow the open loop op-amp, just take this guy and there is a little bit of trick. You have just to you basically have just to put a sort an open loop configuration. So let's use just O without nothing. And let's run. Let's run with the AC analysis. 100 points of decade, starting frequency 1 and stop frequency 10 MHz. I probably missed the node. I wonder where. Is it him? Ah, so the problem is in the power supply. Am I right? Ah, no, this is a comment. Okay. Something very idiotic. So now you see that the gain here, let me cancel the phase. So now you see what I told you on LTSPICE. Here, as you increase the gain, let me put 1 kilo ohm because the gain is going negative. Even less. So here, as you increase the gain, the bandwidth is gonna reduce. Here instead, the bandwidth is not gonna reduce. So you can clearly see the difference. In the first case, you see that when I increase the gain, the bandwidth is gonna reduce because this is the classical op-amp. This is the classical op-amp voltage configuration. So you can't possibly imagine that to employ a configuration which you have a very high gain because the bandwidth is gonna be reduced. Instead, in a current feedback configuration, you have exactly as I told you, something like this, and this is the reason why you choose. Designer choose to use the current feedback on this kind of INA because it has larger gain. Now, if you open the datasheet of the INA, which I already did for you, if you open the datasheet of the INA and you look at the gain, you will see exactly as I told you. This is the reason why you don't lose the bandwidth as you increase the gain. As you can see, it is basically constant to 1 megahertz. It is basically constant to at least 1 megahertz for each gain. Now let's come back to this and let's realize also this part of the circuit here, and I will show you that this equation is really gonna work. So this was something about the basically something about the bandwidth. So let's comment this, and let's also comment this. If I run the simulation, will it make an error? Probably. I can't find the definition of R. So let me write dot param R equal to 100 kilo, just because I don't want to make any kind of mistake. So now let's realize the other portion of this portion of the circuit. I could use a buck converter already made, but let's for instance take let me order for a bit the circuit. Whoa. And let me do this. Okay. Perfect. So in this part of the sheet, I will do the other part of the circuit. So let me use a 12-volt source, and let me use a load. This let's use the European resistor. Special function. Miscellaneous European resistor. So this will be my load. Let us put I don't know, 150 milli. And let's use the shunt. Let us put 100 milli. Yeah, the load is similar to the shunt, but by the way, these are just random values. And now let's use the input resistor, which we call Rin. Rin1 with 100 kilo. And Rin2, 100 kilo. So we are reproducing not this circuit here, but this circuit here. We can use this Opamp. Yeah, I know. I already explained why these Opamp are important, but just to test the equation, we can use the just the Opamp. Basically, just the Opamp of universal Opamp. So let me again put V plus and V minus here. Now, let us use the MOSFET. A MOS. I want to use... oh, come on. I want to use some MOSFET which is good in the gate charge and also good in the RDS on. Like... I prefer a lower gate charge. Yes, this one. 6 ohm is a bit too much. So let's use this. And let's put the load. For instance, 100 kilo. And let us put the bypass capacitor, a filter capacitor of 1 nano. So what is gonna happen is that the load will flow here. So, and you have, let me write the equation, VO equal to shunt times load times Rout over Rin. Now in this case, since the output resistor is equal to the input resistor Rin, you should expect to have the output voltage, let me call out, to be equal to the product of these two. Let me run the simulation. Zoom on this. Delete this. So we have 48 amps flowing into this circuit. And the output voltage is 4.8 volts. I probably missed a 10. I probably missed a 10. Yes, this is a mistake for in my part. So the exact equation is RS times IL over 100 kilo. It is equal to, yes, it should be like that. So now if I decrease if I increase the load, I have 3 volts, and you have and here you have 30 amps. If I lower the output resistor, I have 300 millivolts. So naturally, when everything is fixed, you can decide the gain and everything. So as you can see, I have realized a current to voltage converter with a gain of 10. So in this case, VO is equal to 10 times shunt times load. Without when a route is equal to a in, you have 10 times shunt over load. Naturally, if I put 1 mega ohm here, I will have the saturation, and of course, this is not. Of course, this is not feasible. So I think that aside from this mistake, I think that everything went fine in this video, and let us play with other values. You have 30 amps. Ah no, sorry, it's not that. It's not that it's 10 times shunt times load. It's just that basically I'm stupid, because if I put shunt equal to 1, the shunt is equal to 1 ohm. The equation was right. So it is shunt times load over the ratio. So to have VO equal to load, yes, now it is saturating. So let us put just 1. It is just the shunt gives... yes, it is because of the shunt. Okay. So the equation is correct. You can play with the shunt to have an increase or a reduction. But naturally, if you put a shunt which is higher than the load, so let's return to the proper values, the shunt and the load, and you have 2.5 amps, and the output voltage is 250 millivolts. So VO it is equal to load over 10 in this case. And well, I think that we can stop the video. Thank you guys for your attention, and see you in into the next one.